In this video, we're going to talk about the limitations of the Newton-Raphson method. In the previous videos, I've covered already the Newton-Raphson methods and the convergence criteria and some of the common convergence issues. What if I already used everything correctly? I've applied the correct convergence criteria and I've taken care of all the boundary conditions and avoided all the common convergence issues. Can I still run into trouble with Newton-Raphson? This video, I'm going to show you the cases where Newton-Raphson fails. Now, looking back at our equilibrium equation, we have on the left a nonlinear function of A, which represents our internal force of a spring, for instance. On the right, we have our loading, external loading applied to our body. Let's take for simplicity that this external force is independent of A. We do not consider follower load. We have the usual loading parameter lambda. And now, let's say the internal force is a function of A, which looks like this. It has a downward turning after some peak or limit point. Now, if I want to find the equilibrium position subject to a certain level of loading, when the loading level is below this limit point, yes, there is an intersection, and I can use Newton-Raphson to find the intersection. And gradually, I increase the loading, and once this loading is beyond the limit of this internal force function, then I start to have trouble, because I cannot find the intersection between the external applied force and the internal force of the spring. So when I look at the Newton-Raphson iterations, it iterates until where it runs into the limit point and then starts to diverge. We'll no longer find the next guess solution. Unless there is a secondary path where there is an up turning after this downturn, then this I would be able to find through Newton-Raphson some kind of equilibrium position at this branch. So basically, this is a snap-through example where at this equilibrium position, I load level increases to this ft plus delta t, and I cannot find any point along this part of the curve. The next equilibrium position is somewhere here. So in a way, the equilibrium position snapped from here directly to here. So basically, in force loading problems, Newton-Raphson cannot find the equilibrium path beyond a limit point. In such a case, displacement loading is definitely preferred. I'm going to demonstrate to you the same problem with displacement loading. Unless the physical problem forbids displacement loading, for instance, in a creep type of problem or when the loading is by default pressure, displacement loading is always the preferred choice. Taking our nonlinear spring again. Now our spring has this type of internal force with respect to A, and it has a limit point, and we know already that if we were to apply a force loading beyond this limit point, we would not be able to find the intersection between the two curves, and the residue will not be zero, and Newton-Raphson would fail to converge. If I were to apply an equivalent displacement loading, which means that now A becomes my loading, so this becomes known, but the reaction force or the F external becomes unknown. So if I want to plot the same figure, I will be progressively increasing A. Then I want to calculate the unknown, which is the external force, and I simply plug in this value of A at t plus delta t, and then I'll be able to get my solution. So this solution is already at the downward part of the equilibrium path. So there is no problem finding this point. And comparatively, this is why, through this trivial example, displacement loading is able to trace the downward path of the equilibrium position beyond the limit point. However, displacement loading has its own difficulties with a special phenomena called snapback. So imagine that now my spring has some weakness in the middle, and under some tension, this weakness starts to develop into some damage, softening, and starts to localize. The full equilibrium path of this problem would look something like this. It has a snapback type of behavior, which means that if I were to load it under displacement, at this point I would have a sudden drop in reaction force, and my displacement loading would not be able to retrieve this part of the curve. This is a limitation of displacement loading. This type of snapback behavior happens with strain softening, which is the example I've given. It could also happen with thin shell buckling. When we have shell buckling, after buckling occurs, the equilibrium path is actually snapping inside, snapping back a little bit. And this is a secondary buckling, and the equilibrium path is snapping even further inside. So with this type of problem, we cannot use displacement control to retrieve the full equilibrium path. So if we do apply equilibrium displacement controlled loading, we can still find our solution. The solution does not diverge, but we miss a part of the equilibrium path, and we have a sudden drop in reaction force. So in summary, in the first week of the lecture, I have covered what's linear and nonlinear, and I've talked about the different types of nonlinearity, the first one being material nonlinearity, the second one being geometrical nonlinearity, the third one is nonlinearity due to contact, and I've covered the Newton-Raphson methods to solve these nonlinear problems, and we've talked about the convergence criteria based on residue and displacement, as well as based on energy. I've discussed a convergence issue that could be arise due to overglassing, or could be due to a lack of sufficient constraint on your problem. And I've also mentioned the limitations of Newton-Raphson. In the case of force loading, the Newton-Raphson fails to find a converged solution beyond the limit point. And in the case of displacement loading, when you have a snapback behavior, part of the equivalent path would be missed. Next week, we are going to talk about a new type of solution technique, which is called arc length method. And we're going to explain why this arc length method is able to overcome the limitations of Newton-Raphson.